Oh, we got a little different intro tonight. There's a little instrumental work from one of my favorite songs. I wondered just a little pop quiz there if anybody recognized that song through the guitar work there, but certainly will be impressed if anybody nails that one. But today's title is a very interesting one called Euler's Method. It is a BC only topic as we get ready to rock and roll here, and it kind of puts the finishing touch or the cherry on top of our unit with Diffie-Qs and slope fields and all of those solutions that we were trying to find. But anyway, the definition for our Euler's method today is we consider this a numerical approach to approximating, okay? And right off the bat, there's a little bit of bad news. We're only going to be approximating today. It's going to be impossible to find the exact particular solution to a Diffie-Q, but I tell you what, Euler's method's pretty good and it's going to get you really close. Oh, before I forget, you'll notice it doesn't exactly look the way it's pronounced. We pronounce it Euler. And I tell you what, you go to college next year and you know how to, you'll be the only one in your class of 200 that know how to pronounce that correctly, and that'll certainly impress your professor, I assume. But so we're going to work on approximating particular solutions today, and I want to just kind of do an overview of everything we've done in this chapter. And the first thing we said, if the Diffie-Q is first degree and separable, okay, that was the best case scenario. See if we can spell this right here on the spot. So if it was first degree and separable, then we had the capability of finding the exact solution. All we had to do is separate those variables, integrate both sides, yada yada, and we were good to go. We found the exact solution. However, we started to take a look at Diffie-Qs that weren't as friendly. They didn't play so nice. They weren't separable. And we have two methods for approximating, again, that darn word approximating, the solution. The first one we've dealt a lot with, and we said the graphical approach was to construct a slope field, and what that slope field did is it gave us a visual image of what the solutions and all those families of solutions looked like. And today we're going to take a look at a non-graphical approach known as a numerical approach, or called Euler's method. Alright, we're going to spend a little bit of time trying to give you a little conceptual understanding before we dive into our first problem, but overall, the Euler's method is going to give us two things. They're going to give us a Diffie-Q. Okay, you know, dy dx equals yada yada yada. Most likely it's not going to be separable. Okay, it's going to be very unfriendly. If it was separable, we wouldn't waste our time approximating the solution. We'd go ahead, separate the variables, and actually find the exact solution. The second thing they're going to do is they're going to give us what's called a starting point. It's very similar to the initial condition that we've been using before, and it's basically one particular point that we know the solution goes through. F of x sub 1 equals y sub 1. So for instance, using this example down here, perhaps this is our starting point. They may have told us at the beginning that f of x sub 1 equals y sub 1. You know, they might have said f of 1 equals, 3 or something like that. But anyway, that's your starting point. Now, the blue graph represents the actual solution but you got to pretend with me here that we don't actually know what the solution looks like. We have to assume that we don't know the blue graph behaves or looks the way it does. So what we're going to do is we're going to use the differential equation to find the slope right there at 1, 3. Once we get that slope, we're going to write the equation of a tangent line, and we're going to ride that tangent line for a little ways. Okay, and here's where the theory kicks in here. It's like, all right, that tangent line is going to stay very, very close to the actual blue curve for as long as you stay close to the point of tangency. But if you continue to ride that one tangent line, you notice how you start to deviate away from the curve, and you get a bigger and bigger error. So what we do is you say, okay, we're going to call timeout, and we're going to stop right there. We're going to find the x and y value of that point. We'll call it x sub 2, y sub 2. And what we'll do is we'll use the Diffie-Q to find the new slope at that point, construct a new tangent line to redirect us, and I think that's the key word, redirect, to keep us on track so that we try to mirror the behavior of that blue graph. And again, we don't want to take that tangent line too far, or it's going to shoot us way away from the original curve. So we stop, we call another timeout, and we say, you know what, we find that x and y coordinate. It might be x sub 3 comma y sub 3, and Again, we use the Diffie-Q to find its slope, and we construct yet again another tangent line, and we continue this behavior in an effort to stay as close to the real curve as we can. What's going to improve our accuracy? I think that's a great question to pose right now. What would improve our accuracy? You'll notice right here that gap between the red and the blue represents our error. Okay, basically the quicker we stop writing that tangent line. For instance, what if I said I'm only going to go halfway and I'm going to stop right there and do a new tangent line? And again, maybe on this one, maybe I stopped halfway and redirected myself right there. The gap between those points right there is called our step size. Okay, we usually use the letter H to represent our step size. The smaller you make your step size and the quicker you redirect yourself, okay, the more accurate Euler's method is going to be. Okay, one more step stab at trying to establish some conceptual understanding here. I want to assume, what if they told you ahead of time that f of 0 was equal to 1? And so you knew you were starting right there, and they wanted you to try to approximate f of 2 using perhaps, we said we use the letter H, using a step size of 0.5. Okay, so what you would do is you would construct a tangent line here at this point, and let's see, you would take that tangent line about this far, okay, and then you would stop there. You would find the new xy value. You'd construct another tangent line that kind of follows that little arrow that you just landed on, okay. What you would do is you'd take that, so far, then you'd stop and you'd redirect yourself, and then you'd stop and you would redirect yourself until you got to a point where you thought x was equal to 2, and so this is your approximated value right there, okay. How close is it? Well, right here is your exact value, and the difference between those 2 points represents the error that we've created, okay. What's going to improve our accuracy? What, yet again, if we make this, maybe we change our step size to 0.1. Boy, that would be a lot of work, but in the end it'd be worth it. We'd end up redirecting ourselves much earlier on. We'd maybe go this far, redirect, 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 and I tell you what, you would really hug that original curve. There would be some error, but by golly, you'd be really close. It'd be a lot of arithmetic work, but it would pay off with a great approximation. Okay, we're almost ready to start our first problem. Now notice when you go to write the equation of a tangent line, we're using the model point slope form, y minus y sub 1 equals the slope times the quantity x minus x sub 1. And we could say that y minus y1 is really the change in y's value. We could say that slope is really just another way of saying dy dx. And then right here, x minus x sub 1 is the change in x's value. Okay, so what we're going to usually do here today is, dy dx represents your Diffie-Q, and whatever Diffie-Q is given to you can be substituted directly into that spot. And then the change in x's value is another way of saying your step size. Okay, and like I said, we're usually going to use the letter H to represent your step size, and I cannot emphasize this enough. The smaller H gets, the more accurate your answer is going to be. Okay, we're finally ready to jump in and try to solve one of these problems and get a feel for the way it's going to be worded on the AP exam. First thing they might say is, what if my Diffie-Q said that dy dx equals x minus y? And right off the bat, I think you'd agree that that's a non-separable Diffie-Q. There's, no matter how hard we tried, we would never be able to find the exact solution with the methods that we've been taught so far. And the fact that f of 0 equals 2. So right there's your starting x and your starting y value. They want us to use Euler's method starting at x equals 0 with 4 steps of equal size to approximate the value of f of 2. Now the first thing you have to decide is that, well, if you're starting at x equals 0 and you got to get all the way to 2 with 4 steps, then each step is going to have a size of 1/2. Now I have a table of values that's very, very methodical yet extremely effective, and as long as we stay organized, we're going to be in great shape, okay? In my table, the first thing I always do is I just start off with the given x and the given y value. I like to reiterate the value of h each time just to remind myself to make sure I don't make any careless mistakes. And then I'm going to take advantage of that point slope form that we just kind of modified, where we said, you know what, the change in y is going to be equivalent to my slope, which for this particular problem is the diffy q x minus y, times the change in x, which is always going to be the value of h, or your step size, right there. And then the last column is perhaps the easiest. All we do is say that our new y value, see if I can squeeze this in here, is equal to my old y value plus the amount that y has changed. Okay, and I think we're ready to start doing some basic number crunching. So for my first tangent line, it's going to be tough to visualize this, and I want you to try to keep in mind those first couple of pictures we showed where the series of tangent lines stayed fairly close to the original curve. The x value of 0, y value of 2, substitute them in here, 0 minus 2 times 1/2. I end up getting negative 1 right there. So my new y value is equal to my old y value plus the change in y. And all I'm going to do is I'm going to loop that value, which turns out to be 1, I'm going to bring it down and add that to for my next row. Okay, and now my new x value is very predictable. We know that the x value is going to increase with a step size of 1/2 each time, and you could go ahead and fill in the rest of your this column. We know that the next x value is going to be a 1, and the next one is going to be 3/2, and then the last one, if we slide up here just a little bit, the very last x value is going to be a 2, hopefully. All right, we know the step size is guaranteed to be 1/2. We know that the change in y is going to be my x minus my y times the h value. Let's see, negative 1/2. How about negative 1/4? Negative 1/4 is the change in y. So my new y value is going to be my old one plus the change. So that's going to be 3/4. And all I'm going to do is grab that rascal and loop it down into the next row here. So my new y is 3/4. Step size is locked in. Again, you could just go ahead and fill in the rest of the column with those. Like I said, very tedious, very number crunching here. My x value minus my y value. Let's see. Hopefully you can read at least some of this. It's getting a little messy. Let's see. It looks like 1/4 times 1/2 is 1/8, I believe. Okay. Take my old y value and add my change in y. And this is a very common occurrence. I'm not going to let you use your calculator, and you still got to get these common denominators in your head. So 3/4 is really 6/4 plus 1. I'm sorry, 3/4 turns into 6/8. Misspoke there. And plus 1 would be 7/8. And I'm going to whip that down, and that's my new y value. We got one more row to go. I think we can finish it off here. Delta y is going to be the 3/2 minus the 7/8 times the 1/2 right there. Oh my goodness, no calculator. 3/2 becomes 12/8, I believe. 12 minus 7 is 5/8. 5/8 times 1/2 would be 5/16. So let's see, the old y value plus the 5/16. Let's see, the 7 turns into a 14. 14 plus 5 is 21. Uh-oh, let's see, did I do... Anyway, I think I'm getting 19/16 right there, and if I'm doing something ridiculously silly here, you can laugh at me tomorrow. But anyway, so we'll carry that down, and you'll notice at this point we are now done. We're saying right here that we believe that f of 2 is approximately, now that would be very bad to use an equal sign there. We're saying that it's approximately 19/16, and according to Euler's method with a step size of 0.5, that's what we're sticking to. Okay, here's our last example for the night. I've got, don't have this one quite worded as nicely as the last one, cheating a little bit, but they said they presented me with this diffy q, and this one ironically is separable, but they're just asking us to estimate or approximate a solution using Euler's method, so we'll go ahead and stick to their plan. They said that f of 1 equals 4, and they want us to approximate f of 1/2. Notice something very interesting is happening here. We're going from x equals 1 backwards to x equals 1/2. So when we talk about our step size right here, our step size, using 2 steps, is going to be negative 1/4, okay? Which is going to be kind of interesting. Let's see here. What else we got? We know that the change in y, and I think this is the most important column by far, is going to be your slope, okay, times your step size. which is locked into negative 1/4 each time. Okay, and then that new column is simply where we calculate our new y value. All right, and I think we're ready to rock and roll. So we know that the first x value is 1, the first y value is a 4. We could say that our change in y is going to be 4 minus 2 times a negative 1/4. Oh boy, let's see, 2. How about negative 1/2? Whoops, that's all. Should be a 1 1/2, and then, oh boy, probably cannot read that, but I should say negative 1/2 right there. And then I'm going to say that my new y value is going to be, let's see, 4 plus a negative 1/2 is going to be 3.5, which is like 7/2 if you like fractions. And all I'm going to do here is I'm just going to swing that rascal down. So my new x value is actually 3/4. The new y value is 7/2. And I would strongly encourage you to hit the pause button right about now. See if you can finish off this next row on your own. Come on back and hit play and see if you got the same approximation I did. Okay, here's how it went for me. I ended up with a delta y of negative 3/8 right here. I added that to my previous y value of 7/2. When I combined those two terms, I ended up with 25/8. So based on this information right here, I could then say that we believe that f of 1/2 is approximately 25/8. And that's the story we're sticking to. So there's 2 examples, and hope it goes well. We'll practice some more tomorrow. We just got to be real careful with our arithmetic. We'll get real organized and hopefully be able to visualize a little bit of what we're trying to accomplish. Take it easy. We'll see you tomorrow.